Today we are going to learn about cross-validation, a key to combat underfitting. We'll explore essential cross-validation techniques like K-fold and leave one out, which are crucial for optimizing machine learning models and ensuring robust results. By the end, you'll have the skills to implement these methods in Python and analyze their outcomes.
Welcome to our video on cross-validation, a key to combat underfitting. Underfitting occurs when a machine learning model is too simple to capture the underlying patterns of the data, resulting in poor performance. One of the primary solutions to this issue is cross-validation, a technique used to assess how the results of a statistical analysis will generalize to an independent dataset. It is essential for optimizing model performance and ensuring robust results. In this video, we will explore various cross-validation techniques and guide you through their implementation and analysis.
Underfitting is a common issue in machine learning where a model is unable to capture the underlying trend of the data. This typically happens when the model is overly simplistic, leading to high bias and low variance. Causes of underfitting include having too few features, an overly simplistic model, or insufficient training time. The impact of underfitting is significant as it can lead to inaccurate predictions and poor generalization to new data. Detecting underfitting often involves observing the model's performance on both the training and validation datasets. Real-world examples can include predicting housing prices with a linear model that doesn't account for complex market dynamics.
Cross-validation is a statistical method used to estimate the skill of machine learning models. Its primary purpose is to assess how the results of a statistical analysis will generalize to an independent dataset. By dividing the data into training and validation sets, we can evaluate the model's performance more reliably. The basic cross-validation techniques include K-fold cross-validation, leave one out cross-validation, and stratified cross-validation, among others. Each method has its strengths and is chosen based on the specific problem and dataset characteristics. Cross-validation helps prevent overfitting, ensures more robust model evaluation, and provides a clearer picture of the model's predictive capabilities.
K-fold cross-validation is one of the most popular techniques used to validate the performance of machine learning models. It involves dividing the dataset into K smaller sets, or folds. The model is trained using K one of the folds and validated on the remaining fold. This process is repeated K times, with each fold used exactly once as the validation data. Choosing the right K value is crucial. Common choices include 5 or 10. The implementation involves iterating over the folds, training the model, and calculating the performance metric for each iteration. K-fold cross-validation helps in preventing overfitting by ensuring that the model performs well across different subsets of the data.
Leave one out cross-validation, LEAV, is an extreme version of K-fold cross-validation where K equals the number of observations in the dataset. This means that each observation is used once as a validation set while the rest form the training set. LEAV is simple to understand and implement but can be computationally expensive for large datasets. It provides an unbiased estimate of the model's performance but can have high variance, especially for small datasets. LEAV is beneficial in scenarios where the dataset is small, but it may not be the best choice for larger datasets due to its computational cost. Selecting the appropriate cross-validation technique depends on several factors, including the size of the dataset, the complexity of the model, and available computational resources. K-fold cross-validation is generally preferred for larger datasets due to its balance of computational efficiency and performance estimation accuracy. For smaller datasets, leave one out cross-validation might be more suitable, although it requires more computational power. The choice of technique also affects the bias-variance trade-off. LEAV tends to have lower bias and higher variance, whereas K-fold provides a good balance. Understanding the specific problem and dataset characteristics will guide you in choosing the right cross-validation technique.
Implementing cross-validation in Python is straightforward thanks to libraries like scikit-learn, which provide built-in functions for various cross-validation techniques. To perform K-fold cross-validation, you can use the fold module from scikit-learn. The process involves loading your dataset, initializing the cross-validation iterator, and then iterating over the dataset to train and validate the model. Code snippets help illustrate the implementation process, demonstrating how to handle different datasets and potential challenges along the way. Learning to implement cross-validation in Python equips you with the tools to assess model performance effectively.
Analyzing the results of cross-validation is critical to understanding the performance and reliability of your model. Key metrics to consider include accuracy, precision, recall, and F1 score. Interpreting these scores allows you to identify strengths and weaknesses in your model, guiding further improvements. Visualization tools can aid in comparing performance across different folds and techniques. By analyzing cross-validation results, you can make informed decisions about model adjustments, whether it involves feature selection, hyperparameter tuning, or trying different algorithms. This analysis ensures your model is robust and ready for real-world application. Adhering to best practices in cross-validation ensures accurate and reliable model performance assessment. It's crucial to avoid common pitfalls such as data leakage, where training data inadvertently influences the validation set. Ensuring data integrity through proper dataset splitting and pre-processing is essential. Balancing model complexity helps prevent overfitting and underfitting. Maintaining consistent testing environments, including software and hardware configurations, aids in reproducibility. Continuous evaluation and refinement, based on cross-validation outcomes, lead to model improvements over time. By following these best practices, your cross-validation efforts will yield meaningful insights and drive successful model deployment.
Despite its advantages, cross-validation is prone to common mistakes that can compromise model evaluation. Overfitting to validation data occurs when a model is overly tuned to perform well on the validation set, sacrificing real-world applicability. Ignoring data stratification, especially in imbalanced datasets, can lead to misleading performance metrics. Incorrect dataset partitioning, such as not maintaining temporal order in time series data, results in unreliable results. Misinterpreting cross-validation outcomes, such as confusing metrics or overvaluing certain scores, can lead to poor decision-making. Lastly, neglecting computational efficiency by choosing overly complex validation schemes for large datasets can waste resources without significant benefits.
Cross-validation plays a vital role in the deployment of machine learning models across various industries. In healthcare, it aids in developing models for disease prediction and diagnosis, ensuring they generalize well to diverse patient populations. In finance, cross-validation helps create robust models for credit scoring and fraud detection. By providing a reliable assessment of model performance, cross-validation influences decision-making, guiding resource allocation, and strategic planning. Its integration into machine learning pipelines ensures continuous evaluation and improvement, maintaining model relevance and effectiveness. Understanding cross-validation's real-world applications highlights its significance in delivering impactful solutions. In conclusion, mastering cross-validation techniques is essential for developing robust machine learning models that combat underfitting. We've explored the definitions, methods, and applications of cross-validation, equipping you with the skills to implement and analyze these techniques effectively. Remember, the choice of cross-validation method impacts your model's performance and reliability, so choose wisely based on your data and resources. We encourage you to continue learning and experimenting with cross-validation in your projects, applying the knowledge gained today to enhance your models. Thank you for joining us on this educational journey.